today is about linear transformations, which are the verbs of linear algebra. If vectors are the nouns, then linear transformations are the verbs. And broadly speaking, most mathematical disciplines can be characterized by what are the nouns that we're studying and what are the verbs that give those nouns actions and relate those nouns one to another. So linear transformations are the main object of study, not just today, but for the whole rest of our course. So we're going to get an introduction to what linear transformations are. The basic idea of it is that linear transformations are the right kinds of functions with which to do linear algebra. And they're the right kinds of functions because they, what we say, respect the structure of vector spaces. And the structure of vector spaces refers to its algebraic structure. So those 11 or 12 axioms that define a vector space primarily define an addition operation and a scalar multiplication operation that get to count as those operations for a vector space. That structure, when we have functions that respect that structure, then those functions are the ones that we want to study. And yes, linear transformations are the reason that we call this study linear algebra, as opposed to other kinds of algebra where we might be able to study functions that operate on other algebraic structures. When you take abstract algebra, for example, your objects, rather than being vector spaces, will be simpler algebraic objects like groups, for example. And functions that respect group structure are called group homomorphisms. And so when you study group theory, it's the study of groups and group homomorphisms. Linear algebra is vector spaces and linear transformations. Calculus is the study of the real number line and differentiable functions on the real number line, if you like, or integrable functions, depending on if you're doing differential or integral calculus. Multivariable calculus is the study of n-dimensional real space and, differentiable functions thereof. And so, yeah, what we're doing, formally speaking, is establishing what mathematicians call a category in which we work. And category is just what are my nouns, what are my verbs for linear algebra, it's vector spaces and linear transformations. So that introduction is going to feel a little bit theoretical because we're going to actually get into some examples of vector spaces that are not just arrows drawn in a Euclidean space. So our examples like polynomials, vector spaces of polynomials, are going to come back to haunt us when we try to really wrestle with what linear transformations are, what's their algebraic essence. Because this whole chapter is about the algebraic properties that linear transformations have. One of the most important algebraic properties that a linear transformation has is going to be our third topic for the day, which is to discuss the image of a linear transformation, which is nothing more than the same thing as range when we talk about range of a function in ordinary algebra class. Image is just the fancy name that we give to the range of a linear transformation. And then the kernel of a linear transformation. As the name suggests, the kernel kind of tells us what is kind of at the heart of my linear transformation. And it's at the heart of a linear transformation because it tells me what that linear transformation is shrinking away. What is it collapsing down to zero? So what is the stuff that gets mapped to the zero vector by my linear transformation? That stuff is called the kernel of our linear transformation. So probably most important things to know about a linear transformation are its image and its kernel. But then our computation break that's going to come in the middle is going to be our introduction to how linear transformations are related with matrices. So how can I attach a matrix to a linear transformation so that the matrix can do all the same work that the linear transformation does? This is probably one of the most valuable things about linear algebra, is that for every linear transformation, once we select a basis on its domain and its codomain, we can get a matrix that is nothing more than just, an array of numbers. So far, we've only used matrices as like a bookkeeping tool, as an augmented matrix to do row operations on. But it's so much more than that, we discover today, because a matrix, once we decide how it operates on vectors, can do all the same stuff that a linear transformation, which is defined by some weird formula or maybe something written in words or something like that. If I can define it as a matrix instead, then that matrix can do all the same work that the linear transformation does. And that's what we're going to call the fundamental theorem of linear algebra when we get there today. That's how important that result is.